Good afternoon. This is your lecture 13, Analog Microelectronic Circuits. And in today's class, we will start with the amplifier configurations of MOSFET. So to start with amplifier, we already have the prerequisite done in the previous class. We have discussed about small signal models, or we have discussed about models that is used for analog design. Right. So we will start with MOSFET amplifier configurations. MOSFET amplifier configurations, right? So what we are exactly looking at here is, I know that I understand, or we understand the operation of MOSFET. We understand the biasing. We also understood the region of operation. Now, how can I use this MOSFET for some applications? The very common, very simple application of a MOSFET is to use it as an amplifier, especially in analog circuits, right? So with that, we will just look at MOSFET. So this is the symbol of MOSFET. And even though it is a 4-terminal device, for the discussions now, I will consider it as 3-terminal, assuming that body is shorted to source. So now this is your drain, this is your gate terminal, and this is the source terminal. Right. Now, I can use this MOSFET as an amplifier. Now, what is an amplifier? Say if I look at a box, and if I'm calling it as an amplifier with some specific characteristics, suitable characteristics. Now, this amplifier will be having one input and one output. We call this as ports, right? One on the input side and other on the output side. So this we call as input port, and the other side we call it as output port. So why do we use this ports? We can connect a signal only if you have ports. So this kind of devices we call as 2-port devices, right? There are 2 ports. One is input port and other is output port. So I can connect a signal here. I can connect a signal here. For that I need 2 terminals, and I can actually take an output from this point, maybe across the load resistance. For that also I need 2 terminals. Now, if I look at this, I understand when you apply a signal, you apply with respect to a common voltage, and the common voltage here is actually in fact ground voltage, or ground. We call it as ground. Similarly, when you connect a resistance over here, again you are measuring the output voltage here. That also, the measurement also is done with respect to some common or a reference point. So reference point is always marked or considered as ground, right? So this gives us the understanding that if you have a 3-terminal device, I need to have one terminal as common, or one terminal as a reference point, or one terminal as ground in order to apply input and in order to take, or in order to collect the output at the other side, right? So when you have 3 terminals, we can suitably decide which can be input, which can be output, and which can be ground, right? So now I'm asking a question. You have a 3-terminal device. So how many different combinations I can have in this case? That means one can be input, the other one can be output, and the third one can be a ground or the common reference point. So how many combinations are possible? Can I get some answers in the chat box? I hope you understand we need 2 ports, one at input and one at output, and for both the input and the output signal, we can apply signal and we can measure signal with respect to a reference point. Yes, and that we consider as a ground point. Yeah. So there are 6 combinations. Yes, Lakshya is telling about 6 combinations. Manikandan is telling that there are 3 combinations. Again, Pradyumna 6, Naman 6, Kirtana 3, Muhammad Akram 9. Maunam Mahadev 6, Kartikeya 6. Okay, so 3, 6, 9 are the combinations, right? 3, 3. Okay. Okay, so my question was very specific. I asked how many combinations are possible. So I did not ask how many are valid from that, right? Maybe you guys would have gone one step ahead. So if I have 3 terminal devices, the possible combinations I will just draw. One is I can actually connect input here to the gate. I can take output from drain. I can keep source terminal as common or source terminal as ground. This is one combination. If you provide input to gate, output from drain, and source is kept common, right? Or the second combination can be I can give input to the same terminal gate. Instead of taking output from drain, I can try output to take from source as well, and I can keep this as a common point or the reference point, right? So I tried both with by providing input to gate. Now let me try by providing input to source. Input is given to source, so here it is input, and I am taking output from the same point, and this I am keeping it as a reference or the ground point. This is one. Then let me use some different color. So MOSFET, again input I am giving to source itself. Instead of taking output from drain, I will make this as common and I will try output from here. That is one. Then one more combination can be this, where I will try input. Yeah. So I have tried input at gate, two combinations, input at source, another two combinations. So what is left is this, where I can take apply input to the drain, and I can take output from the source by keeping, all right. So input to here, input to here. Now input to drain, output from here. This is common, or one more last can be input here, output here, and this as common, right? So since you have three terminals, I can have these 6 different combinations, right? Now, so your answers are right. Many have written 3 and many have written 6. So 6 combinations are possible, but out of this, how many are valid combinations, or how many I can use as an amplifier configuration? So so instead of explaining which can be used, I will explain which cannot be used, right? So now if I look at this one, where I have, you can see this one, right? So here I am giving input to the gate, sorry, source, and trying to get output from a gate, which is not possible at all, for the reason we know that gate terminal is always isolated from the rest of the device. So we cannot get any signal or any current passing through this oxide, right? So for that reason, this is not a valid combination, or this cannot be used as an amplifier. One. Second is providing, again, so if gate cannot be taken as an output, then this also can be ruled out, right? This also can be ruled out. Now okay, let us check from this side. Giving input to gate and taking output from drain, that is possible, and since source is kept as common, we call this as common source configuration. That means source terminal is common for both input and output. That means we can apply a signal like this, and we can take output from this point like this. That is the meaning. Similarly, the second case, you can apply gate input to gate and take output from source, and drain can be common. That is also possible, because I am not finding any problem in having this, because you will definitely get a current at the you will definitely get a drain current, right? For that reason, this is possible, and we can call this as common drain for the reason that drain is common for both input and output. So how will I apply? I'll apply a signal here, input, and I'll apply and I'll take output from this point. The third one, giving input to source and taking output from a drain with gate common. So we can call this as common gate. This is also possible. Why this is possible? Okay, now in all these three cases, we know that MOSFET will respond to MOSFET will give a current, drain current, whenever there is a change in gate to source voltage. So in this case you have a VGS voltage. In this case also you have a VGS voltage. In the third case also you have a VGS voltage, but actually in the opposite direction. That means your gate is common and input is given to source. Still you have an effective VGS coming into the MOSFET that can produce a varying drain current. So these three combinations are possible, and we eliminated these two, taking output from drain. Now what about this, the last one? So is this combination possible? Can I get answers in the chat box? Or what can be the problem? It won't act as an amplifier. Okay. My question is why? Or giving input to drain and to sensing the output from the other side with keeping the other terminal as common. Yeah, your answers are right. VG is 0. Okay. Uh, that is one way correct, Karthik. But on the other way it is not correct also. I'll tell you why. Yeah. So we know that MOSFET is responding to yeah. Somebody want to unmute and speak?
Yes, sir.
Yeah.
So
Yes.
VGD is not an independent voltage; it's a dependent voltage. So
Yes. True.
you can't do that. It's dependent on VGS and
Yes,
VDS as well.
it should be dependent on VGS. True. Okay. Yeah, that is correct. Even I think Kirtan also has written the same thing. VGS is not there. So one announcement to everyone. So those are not responding here, please don't mind. Or if you see, you can respond in any way. You don't look for the right answers. So your participation is very important, so that I can address to the answers what you're writing. Uh, okay, so some are responding, few students are always responding and a few are not responding at all. So please listen to classes and respond, and I will definitely open for discussion if you have doubt. Yes, Namit, VGS is 0. Yes, we are not actually in this case we are not directly giving any VGS, so we cannot expect that the MOSFET will respond to that. So this is also not a valid combination for several reasons, as we are not giving a VGS and some more that we will see very shortly, right? Now in all these case, in from all these 6 cases we can actually consider 3 as valid, 1, 2 and 3, and we have named the configurations as common source, common drain and common gate, right? Now one thing need to be noted. So again I am making that statement here. So whatever may be the configuration, we are looking for transistor biased to be in saturation. Transistor should be in saturation. That is the underlying the requirement. And whatever small signal models we have developed, that is also very clear that we have developed the model for transistor in saturation, right? Models are developed for transistors in saturation because we want to use MOSFET as an amplifier in saturation region. So even the model what we developed is for the transistor in saturation. That should be very clear. Now moving on, so we understand that these 3 configurations can be used, right? So for quickly to tell about the configurations, if I write the 3 amplifier configurations. So we are slowly moving to circuits. So from device, we are, after understanding the characteristics, after developing models, we are slowly moving to circuits. So you have MOSFET. In the first case, source will be common. We will provide input to gate. That means again that is with respect to ground. So from now on, we will not always connect a source and do like this. We will rather what we will do is we will keep source as ground. Then I will mark here as Vin. The meaning is we are applying Vin with respect to ground, and the source is the ground terminal in this case. Now here, this is the output will be taken from drain by putting a resistance RD there. This is the first case. I am just drawing the 3 cases, but your actual amplifier circuit will not be like this. So here gate is common. I am providing input to source, and again I am dropping a resistance here which is RL, so that this will be your output terminal V out. And the third case, uh, we are keeping drain as common and input is given to gate, and output will be taken from source. This is RL and this is your Vout. And all these three we call it as common source, common gate and common drain. So whatever you are seeing on the screen now is only a view of amplifier without looking at the DC operating condition. That means when I draw like this and I say that this is an amplifier, it is understood that MOSFET should be in saturation. Now how will you make MOSFET in saturation? You have to use biasing circuits, or you have to bias the transistor properly to keep that in saturation. So as we discussed, or as we have taken our class, initially we dealt everything with DC, and then only we started with small signal, or then only we started with applying a signal. So similar way we will also go ahead like that. Once after getting the circuit diagram of an amplifier, we will not mix both DC and AC together. We will do analysis separately. First we will do DC and then we will go for AC. That is for our simplicity, right? But in the actual circuit both works together. For us to understand, we will just separate and do the analysis. Is it all right? I can take few questions now if you have. Any questions? Any questions? Ashwit Kumar, are you there? Ashwit Kumar. Ashwit is not there. Okay. Charan Kumar. Charan Kumar is also not there. Praveen.
Yes, sir.
Okay, you are there. All right. Tanush. Tanush, are you there? All right. Okay. Yeah. So coming to the question, Nandita is asking, how can we? Oh, Charan is there. I'm present. All right. Ashit Kumar is also there. Oh, then why didn't you respond? Okay. So can we provide input through drain if VGS is given? Then will it act as an amplifier? Okay. So the question is, can we provide input to drain? Okay. Drain if VGS is given. Can you give a clarity on that, Nandita? You mean to ask that you have provided a VGS, that again that is a DC or an AC voltage you are talking, you are referring to. So when I say an input is given to drain, then the DC voltage, yes, DC voltage should be definitely there. So DC bias or DC voltage to VDS and VGS should be definitely there. Now if you're applying a signal to the drain, you cannot expect that your MOSFET will give a current for that signal, right? Because we know that the response of the MOSFET to the drain voltage is very less, or that with that we cannot actually go for the transistor with as an amplifier, because the reason is basically your ID is responding to your GM for a signal VGS, right? Whatever we have written as this ID as G0 into VDS, the contribution of this is very small. So I cannot say that this is possible, right? So this is a non-ideality. So whenever there is a drain voltage, your drain current, so you also would have seen that your MOSFET from the CARA. All right. Yeah. So from the CARA, you have seen that MOSFET is acting as a constant current source in saturation. But whenever there is a small change in, or whenever your VDS is increasing, the contribution to the current is, in fact, you can say that your current is not changing. Even in the ideal case, your current is not at all changing for that VDS voltage. Only in the non-ideal case, you can see a minor variation. So with that, I cannot say I can design an amplifier. And because a major contribution is coming from this term gm rather than g naught. G naught is a very small term, or g naught is the quantity itself is very, very small. But Nandita, that is a good question. Probably when I start with amplifier, you will get more clarity on what it means to be an amplifier, right? So even after the discussion of amplifier, if you're not getting, please ask me again. I can give a little more clarity. Is it okay, Nandita? Okay, yeah, all right. So others, I just called names randomly just to check you guys are there. Right. If it is not, so while scrolling, I have seen your names and I just called up. That's all. Okay. So coming back to, we will start with the first amplifier discussion. So let me start with common source amplifier. Right. Now, if you understand common source amplifier, the rest can be understood very easily. Now, if you have doubt at any point while explaining this common source amplifier, please ping or please unmute and ask yourself, because understanding this is very, very important, right? The very basic amplifier circuit. Now, I am starting from a very simple circuit. So I can have a circuit for common source amplifier, even a complicated circuit. Complicated in the sense having many number of components also is possible. So I'll just take this as my first case. So this is case 1, right? So what I will do is I'll take a common source amplifier. So I understand what is meant by common source. That means the source terminal should be made common. Source should be made common to both input and output. Now, how will I apply input? Input can be applied to the gate. So a DC should be there, and on DC I have to apply a small signal. So this I call it as VGS, and this I call it as small VGS, right? Now, so gate voltage, gate DC is done by this this DC source or VGS what I am connecting on that side. Now at the drain side, I cannot directly connect this to VDD or the supply voltage. So what I can do on the other side is I can, in fact, I can connect like this, right? This is what we have seen before, VDS. But if I do like this, I cannot take a signal, or I cannot get any variation of the signal what I'm applying for the VGS, right? I can even mark like this, but how will I get the variation? I can sense the signal through some resistance or some other means. So for that reason, what I will do is I will connect a resistance here, RD, and this end of resistance will be connected to this point. And I will call this as VDD, showing that is a global signal or the power supply. Right. So this is how I can draw. But for simplicity, or from now on, we will try to represent circuits in such a way that it looks very simple to us. It should look simple to us. So to make this simple, I will redraw the circuit. How I will redraw? I will retain this as source. Now this as drain, this as gate. I'll assume that DC voltage is already there. So only on a DC and AC will work. So for that understanding, I will not mark explicitly the DC. But that doesn't mean that this will work without a DC. DC should be there, and it is there. But for our to make the circuit looks very simple, I am just not drawing that, or no, I am not showing that. Right. And I am drawing the resistance RD here, and the other end of the resistor should be connected to battery in this form. But as I told before, we will be marking only like this, VDD. Now the variation or I'll take output from drain. That is what I told in the beginning, right? Input will be applied to, so this will not be VGS. I'll mark this as Vin, but Vin is exactly equal to VGS, right? Are you getting this circuit? Now, so you should definitely ask me this question. Why have I neglected this VGS and not this VDD? I can assume even that, right? Yes, that assumption is true. So whenever we deal with a circuit, first we will check for the operating region. For that, DC voltages should be there. And once we make sure that the DC voltage is there and the transistor is in saturation, even I need not to consider this VDD as well, right? So how will I consider this VDD? If I am considering, so what I did here, VGS is actually there, but in order to nullify the effect, what I did, I made a short there, right? Similarly, if I VDD is already there, but if I don't want to consider that, if I want to nullify it, I will have to short it. So that is one common thing what we do. So from here we will call this as small signal analysis. We are interested to know how this is acting as an amplifier, how it is amplifying signals, not how the DC voltages are coming in. That we already understood before. So for small signal analysis, that means to analyze the circuit in presence of a varying signal or a voice signal or a audio signal, what I have to do first is, the first thing is I will nullify the effect of DC sources. So DC source can be either a voltage source or a current source. Say for example, this is your DC source, say this is VDC. How to nullify? Replace this with a short circuit. But that doesn't mean that your amplifier will work without a DC. For our analysis purpose, we are keeping your DC aside, right? So how can I do that? I cannot simply do something. If I want to nullify the effect, I can short it. That is first thing. Second thing is, if it is a current source, so this is a DC voltage source. Now, if there is a DC current source, such cases will come. So that can be replaced by an open circuit, because I can nullify the effect of a current source only by making it open. If it is closed, that current will flow. Just to nullify the effect, I have to open it. These are the general rules what we follow in order to do a small signal analysis. So from now on, whenever we do a small signal analysis, we will check for the DC voltage, we will check for the operating region, and after that, when we start small signal analysis, we will assume that those sources are not existing. We will not consider the effect of that source. In order to nullify the effect, a voltage source should be short circuited and a current source should be open circuited. So with this understanding, if I redraw the circuit of amplifier, what I have drawn before as common source is grounded. To gate, you are applying input Vin. To drain, I have resistance RD. But this voltage source has to be shorted. That means I will just mark or drag that to ground. And this is the output point V out. Right. Or I will just redraw this only MOSFET using another color. I'll tell you why I am doing that. So what you are seeing on red is your MOSFET, and the other things are external to MOSFET. So RD is external connected, input source is also connected in external. Is this clear whatever I explained till now? Can I get few response in the chat if it is yes or no, or if you want me to repeat? 54 are there. At least I should get few responses. Who can give a response, please give it there. All right, all are putting yes. Definitely I'll open for discussion after just I finish this now. Okay, now I understood DC, I understood the small signal model. Then now I have come to a circuit, an amplifier circuit. Here also I just kept DC aside. Now I want to know how the circuit is acting as an amplifier. That means to understand that, I should bring in the small signal picture of MOSFET. I should plug in the small signal picture of MOSFET here. Just keeping MOSFET here will not help me for anything. I have to bring in the small signal picture of MOSFET here. So I will write here small signal equivalent circuit, small signal equivalent circuit. So I know the equivalent circuit of MOSFET. Now I have to bring in that and then modify that equivalent circuit accordingly based on the circuit given, right? Now this small signal equivalent circuit, we call it as incremental picture also. We call this as incremental picture because we are providing incremental signal. What do you mean by incremental signal? Small change in signals. It is not like we are giving kilovolts together. We are providing an input which is milli or microvolt range. So we are providing small incremental, small varying signal. So we call this as incremental picture as well. Now, to start with, as somebody asked in the beginning of the class, why I haven't brought drain and so for the beginning, for the when we start the discussion, I will assume that lambda is 0. That means I will not take channel length modulation into consideration. If that is the case, I have to look only for this small signal equivalent circuit. Where is that? Yeah, this is the ideal MOSFET model. This is the model I need to look at, right? So okay, let me just explain this. If you are providing a DC VGS, you have to provide, and there will be a DC current for sure. Now, on that DC VGS, I am giving a small VGS. That is now my V in. That means I will actually get a current ID. This is the picture what you should have in your mind. Now I am replacing MOSFET. Since MOSFET is given in red color, I will draw the incremental picture or the equivalent circuit of MOSFET first. So considering this as source, this as drain, and this as gate. At gate, I am having a okay. Let me draw the. So if you have a VGS voltage here, you will have a current GM VGS. This is what I know from the equivalent circuit, right? This is what we have drawn the other day. Yes, this is the equivalent circuit. Same thing I have drawn there. So red MOSFET is replaced by its equivalent circuit, and now I am adding the components, the additional components. So what is happening to source terminal? Source is actually grounded. As per the circuit, I am modifying the equivalent circuit. Now to gate, you have connected a signal. What is it signal? V in. Now to drain, you have connected a resistance. You can draw the resistance like this to ground, or rather to make it neat, I can draw this resistance like this to ground, and this is RD. Now from where you are taking output? From drain. That means from here only you can take the output. Are you guys getting what I have done? For the circuit of common source amplifier, I have replaced the MOSFET with the small signal picture or incremental picture and modified that circuit depending on the components and the sources connected to the circuit. Still, I did not consider DC because I am doing only AC analysis. This we call as AC equivalent circuit or small signal equivalent circuit or AC analysis, or whatever names we can give. Is that fine? Okay, probably I'll just finish this and I'll take questions. Now, what I'm going to do now, I told that I have drawn the circuit of an amplifier and I want to know what is the amplification factor or what is the gain of this circuit, right? So that gain can be called as small signal gain. So I am interested to know what is the gain of this circuit. So that gain is called as small signal gain. What is that gain? That gain is V out by V in. That is a small signal gain of the circuit. Right. So V out is the output point here and V in is actually the point here. Now how to write gain? So I should know what is V out, I should know what is V in, then you can take the ratio of that. So let me start like this. Let me write what is V in first. What is V in? V in is connected to the gate with respect to source. So V in is same as VGS. Right. Now what is V out? V out is actually the voltage across RD. So whatever V out can be marked as plus minus if there is a current flowing in this direction, right? Or V out will be always measured from drain with respect to ground, right? As V out. So what is V out? V out is current flowing through RD into RD. I can write that V out can be written as current flowing through RD into RD. Why I am using small letter I is because the current is a small signal current. Now if you look at the circuit, I understand that this current is actually flowing in this direction, right? The only current here I can see is GMVGS and that is flowing in this direction. That means if the current is in this direction, you will have a potential like this plus minus. Now what is V out? I can write V out as current is minus GMVGS into RD, right? But what is VGS? VGS is V in. So I can replace this as V out equals minus GM into V in into RD, or if I take the ratio V out by V in, I can write this as equal to minus Gm into Rd. Right. This we call as the small signal gain of the circuit. It is gain, but it is gain for the small signal, so we call it a small signal gain. We generally define it using AV, the same notation what we use for generally for gain. Is that all right? So this is gain. So generally we look for three features of an amplifier. One is gain. So gain we have written here. Gain is AV, and AV is equal to AV is equal to minus Gm into Rd. Now two more things we will look at for any circuit. One is Rin and one is Rout, the input impedance and output impedance. Can you tell me what is the input impedance of the circuit? There are methods to find. So, but I can say that the input impedance here is infinity because nothing is connected between gate and source, and that is the point where you are applying input. So input, since it is applied to gate, I can consider as infinity because input resistance is input voltage by current, but input current is gate current is 0, that means your input impedance is infinity. What about output resistance? If you look at the circuit, your output resistance is the resistance across the output terminal. What is that? It is same as Rd. Right. All right. I hope you got a clarity on this. So if you understood this as case 1, so here actually we haven't considered lambda, we consider lambda as 0. Now if you understood this, can you try a second case, case 2, where lambda is not equal to 0, and can you tell me what is AV, Rin and Rout? Okay, before doing that, I just want, if you have doubts, you can discuss it now. Okay, I'll only explain this. What is lambda not equal to 0? So what will be the difference here? If lambda is not equal to 0, in the equivalent circuit there will be a small difference. What will be the difference? You have to add resistance R naught, right? So just I'll do that. So you will have this as gate, this as drain, this as source. Source should be this as source. Now I have to draw this. This is GM VGS. If you have a VGS voltage applied here, and at this node you will have a resistance R naught. This is the equivalent circuit considering lambda not equal to 0, and this is for MOSFET, which is drawn in red. Now in blue I will modify this by connecting a V in here, by making this as ground, and by making this to RD and giving this as V out. Right. The same analysis you can do. I will write here V in is same as VGS. What is V out? V out is also same, minus GM VGS into, previously it was only RD, now RD and R naught are in parallel, so it is R naught parallel to RD. So what is a small signal gain? New gain is, for the second case, is minus GM into R naught parallel RD. Now what is our input impedance? That is same, infinity. What is output impedance? Previously it was RD, now it is R naught in parallel to RD. Right. These are the cases. So the analysis can be done same as before. Right. So is this clear? Or if you have doubts, you can ask now. It is open for discussion. Okay, so for today's class, I am taking only for only this much. Probably we can go for discussion and then we can wind up.